Hopefully, if you're on this video, you already know how to do a proof by induction, but it seems like a good idea to go over it anyways. We first come up with a statement we want to show is true. Let's call it P of n, where n is typically an integer. Then we show that P is true for the initial value of n. This can be thought of as the starting point of your induction. Then we assume that P of k is true for some integer k. Then finally, we want to show that if P of k is true, then P of k plus 1 is true. And one day, I had a thought. Can we show that P of k minus 1 is true? Feel free to pause and take a moment to think about if this is possible. If we can do this, then we can prove that statements involving the negative numbers are true. Much to my demise, I couldn't find any proofs by induction online involving the negative numbers. So, I've come up with a fairly simple one that involves the sequences 2n and n squared. Looking at the graph, it's pretty easy to see that 2n is less than or equal to n squared for all negative n. But before going into proving this, let's take a look at what's happening for positive n. We can observe that 2n is less than n squared for all n greater than or equal to 2. But even if these inequalities look obviously true when you're graphing them, that's not a valid proof, and we need to formally prove it with induction. Since everyone is probably more familiar with doing proof by induction with positive numbers, let's prove this one first. Our base case is n equals 2. On the left-hand side, we have that 2 times 2 equals 4. And on the right-hand side, we have that 2 squared is equal to 4. So now we have that 4 is less than or equal to 4, which is true. Now that we've shown the base case, let's assume that 2k is less than or equal to k squared for some integer k greater than 2. We need to show that this statement is true for k plus 1. In this expression, if we distribute the 2 on the left-hand side and FOIL out the right-hand side, we get 2k plus 2 is less than or equal to k squared plus 2k plus 1. So, using our hypothesis, we have that 2k plus 2 is less than or equal to k squared plus 2. Now, I was getting a bit of confusion when showing people proofs by induction how I'm able to do this. So let me take a slight detour with a simpler inequality as an example. So we've got 1 is less than or greater to 2. We already know that's true. Now, since I know that's true, if I add 2 to both sides of this inequality, I'm going to get 3 is less than or equal to 4, which is also true, obviously. And to intuitively understand this, you could think of shifting this expression around on a number line. So as long as you're adding the same number to both sides of an expression you already know is true, you're going to come out with another true expression. So in the proof, since we're assuming that 2k is less than or equal to k squared, in the context of this proof, that means that this inequality is true, at least for some integer greater than or equal to 2. So, just like the previous example, I'm just adding 2 to both sides of the inequality. Now from here, we can say that k squared plus 2 is less than or equal to k squared plus 2k. Now, the reason we could say this is because for all k greater than or equal to 1, 2 times k is greater than or equal to 2. Now for our final step, we can say, well of course, k squared plus 2k plus 1 is greater than just k squared plus 2k. So now we've arrived at the inequality we wanted to show. Hence, by mathematical induction, 2n is less than or equal to n squared for all integers greater than 2. Okay, so now let's move on to the negative version of this proof. For our base case, we're going to start at the first negative integer, n equals negative 1. On the left-hand side, we have that 2 times negative 1 equals negative 2. On the right-hand side, we have negative 1 squared, which is 1. Clearly, negative 2 is less than or equal to 1, so the base case holds. Now, let's assume 2k is less than k squared for some negative k. Unlike the previous proof, we want to show that this inequality holds for k minus 1. Like last time, let's distribute the 2 on the left-hand side and FOIL out the right-hand side. Now, using the hypothesis, we have that 2k minus 2 is less than or equal to k squared minus 2. From there, we can say that k squared plus 1 is greater than k squared minus 2, since 1 is greater than negative 2. Now, here is where it may get a little bit confusing. We can now say that k squared minus 2k plus 1 is greater than or equal to k squared plus 1. Initially, it may look like I'm not supposed to be doing this. If I'm subtracting something from this number, why am I saying that this number is the bigger one? The answer to this requires you to recall what we said in the assumption. K is a negative integer. As we learned way back then, a negative times a negative is a positive. So deceptively, minus 2k here is actually adding a positive number. Nice. Now we've shown by mathematical induction that 2n is less than or equal to n squared for all negative integers n.